just give you a little bit of background on me. I've been with Schneider Electric, or Foxborough as it was, 7.5 years ago, for that length of time now, and I became the offer manager for the level instrument product range in February of last year, right in the middle of COVID, for a great time to change roles. But for most of my time with Schneider Electric, I've been in sales as a district sales manager for the whole process instrumentation portfolio, and looking after a region known as NESA locally. It's Northern Europe and Sub-Saharan Africa, which basically means the UK, Ireland, the Nordic countries, and largely the English-speaking African nations. But my time with this organisation isn't limited to that, because prior to that I was part of the sister company Eurotherm in their UK sales team for 6 years. So I've got quite a lot of experience with Invensys / Schneider Electric as we are now. And that forms part of a 25-year experience that I've built in automation sales and marketing. I started with sensors and safety, moved into more mechanical automation products, conveying and power transmission, smart vision systems and sensors again, data acquisition and process control with Eurotherm, of course. Now instrumentation sales with Foxborough or Schneider Electric, depending on what you prefer to call us, which brings us bang up to date. As you can tell from my accent, I'm from the UK. I'm Welsh by birth, but I live near Oxford in England, which makes it rather convenient for not only for the Europe sales territory, but more importantly for the manufacturing sites where the level instrumentation is produced, both of which are in France. So it's very easy for me to interface and be on site at the factory when that's required. Excuse me, I'm just going to take a little drink. So that's enough about me. Let's get into the more interesting stuff. So the first question I'm going to pose here is, well, what is a level measurement offer? So what do we have? Well, we have two strands to this. There's the buoyancy level transmitters, which is former Eckhart brand, then Foxborough Eckhart, and obviously now Schneider Electric. But we're not really going to talk about that today. I'm just really showing you that for context in terms of where the radar offer sits within the portfolio. So really, there are two major streams to our level measurement instrumentation package, and today we're going to focus on radar. If any of you are wondering, by the way, if questions, absolutely please ask questions. Put them in the chat or wait till the end, because I'm going to have about 5 to 10 minutes at the end of this presentation where we can go through some questions. And if we overrun, because we get into some good discussions, then all the better. Sorry. So you've seen what we've got, but let's drill down a little deeper into that. Let's not only look at what we've got, but where can we use it? So where can we sell it if you're in sales? Where can you deploy it if you're an end user? Where would you integrate it if you're into systems integration? And the pictures you see on screen here are really just a portion of all the applications we could solve with this instrumentation. So as you can see, we've got free space and guided wave radar instruments that are used for liquids measurements in tanks, in open vessels and open channels. And we've got solids measurements for drums, silos, conveyor belting, stockpiles, and even pressurized containers for liquid measurement also. So I'm going to get into more detail on some of these interesting applications in a few minutes. But before I do, let's actually touch a little bit on the technology that I'm describing today. This is not intended to be, and hopefully won't become, a technical lecture about radar measurement level technology. We've done that before, and I'm sure we'll do that again. The focus today is going to be on those applications. Just to give it all some context, I am going to talk for a couple of slides about why the Schneider Electric Radar level measurement instrumentation is worth investing in, and how it is differentiated from what else is out there. What we deploy in our range of radar instruments is FMCW, that's frequency modulated continuous wave, as opposed to the older, more traditional, if I can use that phrase, pulse burst radar transmitters. And the graphic you're seeing on the screen now really really explains what always used to be the case with radar level transmitters, and for many manufacturers still is the case. You send a pulse towards your surface and you measure how much time it takes to return, and that's how you work out the distance to your surface and therefore calculate your level. All very nice, relatively accurate, non-contact, it does work, but it has its limitations. We prefer to use this FMCW, continuous wave technology, and the important bit is the M of this acronym, the fact that it's a modulated continuous wave. So we are continually pinging the surface with a signal, and because of this modulation of the signal on reflection back to the receiver, we don't measure time of flight. We actually measure the change in frequency, which gives us a much more reliable measurement for the distance to target, and much more immune to any spurious reflections or noise. So this is a far more reliable technology than the old pulse burst method, which is why we utilize it. The benefits you get from continuous wave as opposed to pulse burst, you can see the left and right here, is that you're getting much more frequent reflections, a much larger input of signals into the receiver, so you've got a much more robust and strong signal and a greatly improved immunity to noise. So any measurements you do with our radar range are extremely reliable compared to pulse burst technology, and effectively about 100 times more reliable if you count the number of signals received as a measure of reliability. So that's a little bit about the technology, and as I said, this isn't intended to be a technical lecture, so let's actually, before we get into the applications, have a quick walk through what makes up our range. So first of all, I'm going to focus on the free space radar, right? So that's what the kind of instrument you just saw in the graphic on the previous slide, the kind of thing that is employed in the front or maybe the rear of your car for distance sensing radars on your motor vehicles. So for liquids, we have a range of 4 models here, over 3 different frequency bands. The first model, one of the first 2 models to come into the Schneider Electric Radar range was the LR01, which is a 10 gigahertz radar. And this radar is really still very much a key part of our range, because even though it's older technology to the ones on the lower half of the screen you can see now, it still finds many applications. It has some distinct advantages in some areas, and I'll come on to those later. But the 10 gigahertz range is perfectly suited to measuring static liquids, so storage tanks, water, drums, and not so much process applications, but the more liquid storage. And it's not really designed for measuring solids levels. But a few years ago, about 3 or 4 years ago now, we greatly expanded the Schneider Electric Radar range with the introduction of 24 and 80 gigahertz band radars. Now, in 24 gigahertz for liquids, we have 2 models: the LR54, which I like to think of as our kind of entry level or standard offer. It's the place where I would start if I'm looking at a new radar level application. I'd start with LR54 and work outwards from there. And I'm going to talk more about why I'll do that in a moment. We also have the LR74, same frequency band, so same kind of performance, but a few more features which make it more suitable for more challenging applications. And then to complete the liquid level measurement product range, we have the 80 gigahertz LR75 and 80 gigahertz has a much narrower beam angle and therefore beam width at the surface you're measuring than the 24, and consequently the 24 is a narrower beam than the 10 gigahertz. And you will see in coming slides the difference that can make and sometimes doesn't make. What we couldn't do before we introduced these newer radars about 3 or 4 years ago was measure solids with free space radar, but now we actually have two models that are optimized for this in 24 and 80 gigahertz. Put it simply, the 24 gigahertz model, the LR64, is great for large particle solids, big aggregates, rocks, and that kind of thing. The LR65, 80 gigahertz is really quite good for very fine, dusty environment products like fine sands, for instance, or indeed for materials that have a lower dielectric constant. And while I said this was not going to be a technical lecture on radar measurement, of course, with all of these things, we do have to think about how well your liquid or solid surface responds to a radar signal, and that is measured or dictated by the dielectric constant of the material. The lower the dielectric constant, the weaker the reflection or more transparent it is to radar. And anything below 2 is termed a low dielectric constant material, and therefore we may start to struggle with free space radar, which is where guided radar really comes into its own, because the signal is concentrated physically within the waveguide from the transmitter, as opposed to just emitted from an antenna. You get much more of the signal where you want it to be, and much more importantly, of the signal is returned when it meets a surface of liquid or solid, so you can measure down to much lower dielectric constants. So let's now get into the really interesting bit. At least I find it the most interesting bit, and I hope you will too. The applications where you can solve people's measurement needs with the products I've just walked you through. So what I'm going to do first of all, though, is I'm actually going to do a few exercises on theoretical measurement applications. I have got some actual case studies to show you shortly, but the purpose of this part of the webinar is really to demonstrate the effect that the geometry of your vessel and of your process connection and how those can influence which instrument you choose and also which antenna you pair with it. So let's go through this process. So what we're looking at in this hypothetical scenario is a storage vessel for sulfuric acid. It's 4 meters high by 2 meters wide, so 13 by about 6.5 feet. And importantly, we've got a 2-inch or DN50 flange connection for our process instrument. So what could we choose in our 3 sort of free space radar frequency bands? So obviously it's the LR01 for 10 gigahertz, and this process connection really dictates that we need to choose a plastic wavehorn, a PTFE wavehorn antenna suitable for this 2-inch flange connection. For the 24 gigahertz variant, we have 2 models to choose from, LR54 or 74. And again, the 2-inch connection really takes us towards the metallic horn antenna. And lastly, then, the 80 gigahertz radars, both of which have lens antennas, and a variant of which is available with a 2-inch connection. So let's have a look what that does to our measurement scenario. So as you can see, all 3 devices will adequately measure the level. The influence of the antennas obviously dictates the width of the beam over the measurement range, and as you can see, even with the lower frequency, so the wider beam angle of the 10 gigahertz radar, we could pretty much get close to the bottom of the tank. We may choose to employ empty tank spectrum sort of algorithm, which is available in all of our radars, to enable us to effectively ignore the curvature at the bottom of the tanks to make LR01 effective. But as you can see, the 24 and 80 gigahertz radars both have no problem with impinging on the tank walls, and so both would be appropriate for this application. So which one would you choose out of these? Well, sometimes the answer isn't technical, sometimes it's commercial, and in that I would veer towards one of the 24 or 80 gigahertz devices, for, because I don't want to have anything to do with the sidewalls of the tank. I would opt for the 24 gigahertz LR54 because it's perfectly suited to this application, will give us a good strong signal, doesn't impinge on the tank walls, and the LR54 in particular is the better priced option in these. And obviously what we want to do is not just solve your problem for you technically, but give you the best commercial solution that will do so. So LR54 would be the choice here. So let's have another look at one of these worked examples. It's the same tank dimensions, but this time we're looking at aviation fuel with a lower dielectric constant. It's below 2, you notice. And this time we have a 4-inch or DN100 flange connection on the same vessel. If we choose the LR01, this time with a 4-inch metallic core antenna, we get a little bit more beam spread, a wider beam angle than we had in the previous case. So we may want to consider whether we use this. You can use this device in this application, utilizing the empty tank spectrum software. But I would, again, just like in the previous example, choose to use either the 24 or 80 gigahertz radars. Now, in that, we are nowhere near the tank walls in either case. Again, my cost-efficient mind would say, okay, 24 gigahertz is good enough. Let's go with that. It's lower priced than the 80 gigahertz. And then do we choose the standard version, LR54, or do we choose the higher spec version, LR74? Well, when we look at what we're measuring, and this is aviation fuel, I would opt for LR74. It's a higher price device, but it has a quick change sort of connection, so you can actually remove the transmitter while the device is connected to the process, but it also has, as an extra safety feature, a metal glass barrier between the antenna and the transmitter itself, which gives you an extra level of protection in the event of potential explosion. I think we've got 2 more of these theoretical examples now before we get into the actual case studies. Hopefully you're finding these interesting. This time we're looking at wash liquor, so it's pretty much an aqueous solution, but we've got foam on the surface of the liquid. So this is going to be a little bit more challenging. So yeah, we've got a 4 meter by 2 meter tank, or 13 feet by 6.5 if you prefer imperial measurements. And this time we've got an 1.5 inch threaded connection. So what can we use? So again, we can use LR01. It's available with an 1.5 inch MPT threaded. This time it's a polypropylene waveform antenna. The 80 gigahertz variants, we have a metallic horn antenna with 1.5 inch threaded connection. And for 80 gigahertz, as I said earlier, both the LR65 and 75 have lens antennas. And again, we have a 1.5 inch MPT variant of that. So which is going to be more suitable? Well, it looks to me like in terms of beam angle and beam width, like you could use any 3 of these. Maybe the lower frequency LR01 isn't ideal if you want to measure right down to the bottom of the tank. But of course, we haven't considered the foam. Now, perhaps counterintuitively, the higher frequencies can give you some problems with foam, depending on the density of the foam in question. You may get some scattering of the higher frequency and therefore shorter wavelengths of the radar signal. So actually, the LR01 might be more appropriate. But you know what would be even more suitable for anything with a foam is a guided wave radar, the LG01, where the signal, if you remember what I said earlier, is concentrated within the waveguide, so it can't really be scattered by the foam, so it will give you a good strong reflection off of the liquid surface. And so that would be my first choice. even though you could, in theory, use any one of these devices. So I think this is the last of these theoretical work examples, just to demonstrate the influence of tank geometry and process connection on the measurement. So this time it's sodium hydroxide solution with a reasonable dielectric constant. But this time we haven't got a foam, but we've got an agitator in the tank, which is going to give us an agitated surface. It's the same tank size as before, and we have a DN80 or 3-inch flange connection. So LR01, we would be looking at a metallic horn antenna, 24 gigahertz. It's a drop antenna, and again a lens antenna in 3-inch variant for the LR75 80 gigahertz radar. Now what you can see here is the 10 gigahertz radar has got quite a large wide beam width. We would definitely have to employ empty tank spectrum to not only ignore the stirrer but also the side walls of the tank. You might think, oh, yeah, we'll play safe. We'll make sure we don't hit the sides of the tank. We'll go with the narrowest beam, the highest frequency. But this could potentially give us another problem. When you zoom in, you can see that the ripples on the surface caused by the agitation effectively will act like little mirrors for the shorter wavelength 80 gigahertz radar beam, and reflect much of the signal away from where you want it to be into the transmitter's receiver. So you will get some signal here, but you can get a lot of attenuation of the received signal, so you won't get as much of a strong signal as you'd like. So really, the one of choice here is the 24 gigahertz radar. It doesn't have the same negative effect from the surface of the liquid. The lower frequency would be best, but of course the beam angle is rather wide. So the optimized answer here is the 24 gigahertz LR54 or LR74. Sodium hydroxide. It's not especially explosive. I'd go with the LR54. That gives you the same performance as the LR74. It's the most optimized for this measurement and most cost optimized device also. So you can see there are a lot of factors at play here: price, connection, tank geometry, medium chemistry, and of course other things like agitators and foams. So let's get now, after these theoretical examples, into some real-world measurements that have been done with our range of instrumentation. And the first one I'm going to start with, logically enough, is for what I described as the entry-level or standard radar transmitter earlier, the LR54, one of our two 24 gigahertz liquid level measurement devices, seen here with the drop antenna, which you saw was referred to in one of the previous slides. And what I really like about this drop antenna, it is optimized for lack of buildup of liquid or dust solids on here. Unlike a waveform antenna where you can get a lot of buildup, these are pretty resistant to that. In this application, it's fairly straightforward. It's water in the storage tank in the triple N industry. We can mount the transmitter where we like. We don't have to worry about the sides of the tank. We don't have to worry about agitators or any other furniture in the tank. So really, what we're looking for is a reliable measurement and a value for money solution. And so therefore the workhorse or standard option, the LR54, being a good cost and performance optimized device, is the one that was chosen for this customer, and it's still working well there today. Let's look at the next one. So this is another example where we used the LR54, but in this case you can see there's a low pressure flange protecting the transmitter from the process, and we sell a lot of these low pressure flanges. more for device protection than anything else. And this is in the chemical industry, where rather than looking at tanks of water, it's a similar kind of geometry. Tank isn't quite as wide, but it is certainly not too constrictive. But we're looking at chemicals here which are highly viscous and corrosive. Hence, we're protecting the device with a low pressure flange. This customer had previously used ultrasonic level and found them to be inaccurate and unreliable. So again, it's not too challenging an application. We have good dielectric constant in the liquid level of this chemical solution. So LR54 was again the obvious and logical solution to give this customer a reliable and also cost-effective solution. So next we're going to look at a slightly more challenging one. This is measuring ethanol in a biofuel production plant. So obviously biofuels are very much a growing technology. I think getting increasingly widespread, and we managed to get some level measurement success in this sector. And in this case, we go with an 80 gigahertz LR75 model for a couple of reasons. Well, let's give you a bit of background first. Actually, the customer had been using differential pressure transmitters to measure level, and indeed they still are. They're just using that now in conjunction with the LR75 radar, but they were using that on its own before. And what they found was they, to be able to do any maintenance on the DP cells, they had to completely empty the tanks to get access. Not the case with a radar transmitter mounted in the tank roof. And of course, the advantage with an 80 gigahertz signal is you can have it relatively close to the sidewalls, because the narrow beam angle allows you to do so. But also, if you've got a low dielectric constant medium like a hydrocarbon such as ethanol, then the lower dielectric constant is more likely to be seen by the higher energy, the higher frequency of the 80 gigahertz radars. And of course, they are pretty much maintenance free. Now, let's look at an application for one of our oldest radar transmitters. It isn't all about the newer models today, because as I said earlier, the LR01 was one of the two first models that Schneider Electric adopted about 10 years ago. The 10 gigahertz radar is perfectly applicable in many applications, particularly in water. In this case, we're looking at wastewater. So with 10 gigahertz, we'll get a good signal of wastewater. This is in the electronics industry, as you said, but the real differentiator, the real winning case for this one is the fact that you can buy LR01 as a remote version. So the actual transmitter can be separate from the antenna by a distance of up to 100 meters. Cable connection between, as you can see the cable disappearing up to the top of the tank here. So what the customer was having to do before was send an operator up to the top of the tank to check his level measurement. Very labor intensive, consuming lots of time. So we've saved a lot of that time now. The electronic, the display is at eye level. They can very easily do a manual check if they don't want to trust their control system that is reporting the level correctly. And more importantly, they're also keeping their health and safety officer happy, because people aren't having to climb up to the tops of the tanks to measure to check the liquid level measurements. So that's a novel sort of differentiator, if you will. But remote electronics is certainly an advantage in this case for the LR01. So what have we got next? Yes, we're going to take a little break from the applications now, just to have a little recap of the similarities and differences between the different models in our radar portfolio. So on the left, we've got the LR01, which I just talked about in that wastewater tank. 10 gigahertz measures with an accuracy of plus or minus 5 millimeters up to about 30 meters distance. It will get you to 250 Celsius and 40 bar, or 482 Fahrenheit and 580 psi. And one of the advantages that this model has is its quick coupling. I mentioned earlier, you can remove the top works from the antenna easily while it's still in process, and it has the option for this Metaglass extra safety barrier between the antenna and the transmitter. And this is also true for the LR74, the eagle-eyed among you will have noticed the same thing here, but I'll come back to that in a moment. So the LR54, which I described as the kind of workhorse or entry level of the newer radars, kind of more naturally fills the space that LR01 has been occupying to itself for a longer time in our range, but it does have a higher degree of accuracy over a much greater maximum range. It doesn't go up to as high a temperature rating, and doesn't have the quick connect construction. So you'd have to remove the whole instrument, including the antenna, from the process, and we don't have the Metaglass safety barrier between antenna and top works, which we do have, as I was just saying, with LR74. So again, same performance, it's 24 gigahertz, so same accuracy, same measurement range. It's rated up to 100 bar though in this case. It'll get you 200 Celsius or 392 Fahrenheit. But it does have the quick coupling and Metaglass feature. So let's go now to the highest frequency device available for liquid level measurement, which is the LR75. This will give you similar accuracy and maximum measurement range. It will go up to the same temperature as LR74. You can see there are lots of similarities here. It's rated to 40 bar. And while it, like all of the models you can see on screen here, are SIL2 certified, it doesn't benefit from the Metaglass or quick coupling features of the LR74 and LR01. And then lastly, on the right-hand side, and we're going to look at some applications for these in a moment, we have the solids measurement devices. That's the LR64 in 24 gigahertz and LR65 80 gigahertz versions. And as you can see, horn or drop antennas for the 24 gigahertz variant, and it's a lens antenna for the 80 gigahertz radars, with or without an extension. And the measurement performance is largely similar to the other newer radars, as you can see. So let's get into some more applications now that we've recapped what we've got in our range. Okay, oh sorry, I was forgetting what the slide. We just have a little focus now on our guided wave radar device, the LG01, which I referred to earlier as an option for that tank with foam above the liquid. LG01 utilizes a much lower frequency, but it is all concentrated within the waveguide, so it's still very much applicable for low dielectric constant materials. Up to 40 meters level in liquids or 20 meters in solids. We really sell most of these into liquids applications. It's not truly optimized for solids, but it does do a decent job. It'll be rated up to 300 Celsius or 570 Fahrenheit, down to around -50 or -58, and up to 40 bar or 580 psi. It also has a couple of safety features like anti-blowout, and like every model in the family, is SIL2 certified. And this one, like the LR01, has a remote electronics option. So let's now, like we did with the free space radar, let's try out the guided wave radar in a theoretical example. So this time we've got a 10-meter high, a 2-meter wide tank with a 3-inch or DN80 connection, and we're looking at gravel. So we've got a low to medium kind of dielectric constant for this material. We can't use LR01 at all because it's not for solids measurements. So we can use an LG01 with a guided wave. You need to be careful if you've got really large, dense solid material. Traction loads on a cable style antenna can be a problem. Not so much of an issue though with 24 or 80 gigahertz free space radars, 64 or 65 are the models in question. And really, while any three of those would be a model of choice, I would probably recommend a customer uses the free space radar at 24 gigahertz. Very easy to deploy. We don't need to worry about the cable and any traction loads, particularly while filling or emptying the storage vessel. There's no problem with beam width, so we don't need to go to the more expensive LR65. LR64 24 gigahertz is very much the appropriate device. What we've got next? This time we've got solids with much finer particle size and a slightly lower dielectric constant. So 10 meter by 2 meter vessel again. This time we've got a much bigger connection, precipitation 6-inch or DM150. If we go with 1 gigahertz guided wave or 24 gigahertz and 80 gigahertz free space, you can see that all three will work quite adequately. A single cable antenna is perfectly suitable for this kind of material. We would have consideration for the mass of the solids on filling, as I said in the previous example. The 24 or 80 gigahertz radar are both quite appropriate for this application, but I would select the 80 gigahertz because of the very fine particle size and the fact that the dielectric constant is a little lower than the previous example. We're going to get a much more solid, reliable signal received back into the transmitter with the 80 gigahertz version. Okay, so let's now look at some real-world examples. I don't have a photograph from site of this one, but I do have a diagram taken from the customer's details of his application, and this is in an industry that we're seeing increasing applications for radar measurement, and this is plastic hoppers. So what we have here is PET pellets. This is a low dielectric constant material, but also creates a lot of dust. So we've got two problems here, and this is why we've chosen the LR65 80 gigahertz radar, because it really is optimized for dusty atmospheres. And that combined with a low dielectric constant of the material, the stronger reflection you're going to get from a high frequency signal really dictates that this is by far the best option to choose for this application. So we've got a small radar beam. We focus the energy exactly where we want it. We see through the dust because of the higher energy of the higher frequency signal, and this has worked very successfully in this and many similar applications. Right, now same device but a different kind of application. Again, it is solids, but what we're looking at now is sand in sort of aggregate quarry. And so we're filling a silo from this inclined conveyor of this sort of sharp sand, and we need to guard against, for this customer, silo overfill. So the fact that we have continuous measurement is really important. And again, it's a low dielectric constant material. So again, we choose the higher frequency signal for better signal to noise ratio. And of course, if you remember, with both of the solids radars, we have near flush mounted lens antennas. So we have minimized deposits on the antenna. Okay, so we're just coming towards the end of the presentation part now. Before we get to questions, I just want to quickly walk you through this table, which doesn't just look at radar, it looks at several measurement technologies, all of which are available from Schneider Electric in collaboration with our friends at SFC. You can measure level, of course, as I mentioned in one of the applications, using pressure transmitters. As you saw on one of the very first slides, we also have a buoyancy level measurement system, which we're not really focusing on today. And then we have the radar family, which I've described to you today. Now, there are several things at play, as I mentioned in those theoretical examples. There's the application type. Is it liquid? Is it clean or is it dirty liquid? Is it static as a measurement? Are we changing density? Is there an interface? Is there agitation? Is there foam? Are there solids? liquid, what's the viscosity like? All of these have an effect. And what you will see is that no one measurement technology can measure absolutely everything. There's no column that is completely green. And it really is, to use an old phrase, horses for courses. And what I strongly recommend is, if you have a measurement level application, is to reach out to us at Schneider Electric, or if you're a customer, reach out to SFC, who obviously have the support of many people in the Schneider Electric organization to advise on the right solution for your measurement application. And of course, if this table is available to be shared, should you want it as a ready reminder in the future. So I think that pretty much concludes the presentation. If you do have any questions, please feel free to bring them now. I'm going to unshare the screen and go back to the presentation. We'll go back to the meeting window. Hopefully.
Yes. So John, the one question that we had in the chat, I'll unmute everybody in a second, but the first question we had was, are any of these liquid sensors suitable for explosive atmospheres such as sewer wet wells?
Yeah, yes, they're all pretty much suitable for that. As I said, the two models in the free space radar, which have the metaglass barrier, are actually designed with this kind of application in mind. So that's the LR01 and the LR74. But all of the radar devices I've talked about do have a number of certifications for this kind of applications. So we've got ATEX, ICEX, and I can't remember the end of the other. My mind's gone blank, but certainly, yeah, we do have explosion-proof certifications. Okay. Any other questions?
There isn't any other questions in the chat. I have set it up so you could unmute yourself. I see George already unmuted himself, so I'm sure he has 100 questions for you. George?
Yeah, question on, you talked about a foaming application, which we have a lot of, and then you recommended the lower frequency unit to measure the liquid level versus the 24 or 80 gigahertz to actually won't possibly hit the top of the foam. But if you're not hitting the top of the foam and you have the I guess the chance of overflowing the tank with the foam, would you recommend, if they want to know actually the level from the top, to use the 80 gigahertz to know where the foam level is? Or
well, that's a really good question, because of course measuring the top of a foam is not the easiest thing to do, even with an 80 gigahertz radar, and is much less, you can imagine, gives you a much less reliable reflection than does a liquid surface. So we generally, we don't tend to recommend using these kind of technologies to look for the top surface of a foam level. Of course, you can try it, and it really will depend on how dense the foam is in your given application. So the answer is a partial yes. Really, the only thing I can suggest is to get a device onto site and try it out.
okay, and then with this example that you have right here, is there any kind of rule of thumb on the height of the foam in choosing one or the other, or is it all come down to the density of the foam? And
yeah, it really is the density of the foam that is the determining factor in these situations.
Okay. And then my other question was on basically dual level measurement.
You mean like measuring an interface as well as a top surface?
Correct.
Right. In radar, we don't have the capability to do that. We do have a solution.
Guided? On the guided,
No.
do we?
No, we don't. We don't have an interface measurement with our guided wave device, the LGO1.
Okay.
Buoyancy will measure interface very effectively if it is feasible in the application you're thinking of. Buoyancy is great for interface measurement.
Okay.
And if you want to discuss that, offline, I'm happy to do that with you another day.
Okay, thank you.
No problem. Thanks for the questions.
So there's no more questions in the chat here. So I think that's pretty much it for questions.
Okay, well, look, all I will say in conclusion for my bit then is really to encourage anybody who's on the call, whether they're colleagues or customers, if they have anything that they think of that they want to ask later on, a question that occurs to them, they can, of course, contact me directly. My email address was on that last screen, but of course they can field questions through you and your colleagues at SFC. So either way, I would like to help anybody who has a question or an application, or God forbid, a problem with a level measurement. If I can help, please don't be shy to ask.
Thanks for doing this, John. I appreciate it. All right. Have a great day, everybody. Thanks for logging in. And if you have any questions, feel free to reach out. We'll also send an email to everyone that signed up for the webinar. So we'll go from there. Thanks again.